Welcome to Engineered for Impact, a podcast helping engineers learn and think more about how they can have a positive social impact with their careers. In this episode, I talked to Vivian Belenky, a research fellow at Convergent Research. Convergent Research incubates focused research organizations that are designed to address specific bottlenecks in a scientific field. Recently, they've been investigating the use of ultraviolet light for reducing the transmission of pathogens in indoor environments, specifically looking at Far-UVC. This technology could help safeguard humanity against the next extreme pandemic while also reducing the prevalence of the common cold and flu. Vivian's recent work has focused on road mapping the state of Far-UVC technology, and that's the focus of today's discussion. We cover how Vivian came to work in biosecurity and specifically on indoor air quality. We go over a brief history of germicidal ultraviolet radiation and the current state of Far-UVC technology. We talk about what is required for Far-UVC to be adopted in a broader context and some of the safety considerations around the technology and pathways to reducing its cost. Finally, we discuss how engineers can effectively contribute to developing the technology and promoting the widespread adoption of Far-UVC. You'll find show notes with valuable resources related to this episode and ways to support the podcast at engineeredforimpact.show/Vivian. That's Vivian. Vivian and I dive straight into the discussion on this one, so I'll provide a quick primer on indoor air quality. Air quality inside buildings or the built environment is typically the focus of HVAC engineering. HVAC stands for heating, ventilation, and air conditioning. Traditionally, good indoor air quality is a byproduct of optimizing HVAC systems to deliver sufficient fresh air to an indoor space at comfortable temperatures and humidities. In this episode, though, we're using a slightly broadened definition of air quality, one that includes the concentration of airborne pathogens, which could be harmful to people occupying the built environment. Under this definition, improving indoor air quality also includes reducing the transmission of airborne pathogens between building occupants, not just maintaining comfortable temperature and humidity levels. And this is where Far-UVC comes in as a technology that can disinfect the air and reduce the spread of pathogens in an indoor setting. That's all you need to know for now. If you enjoyed this episode, please head to the website and leave us feedback or share the episode with a friend or colleague. So, without further ado, here's Vivian.
I'm Vivian Belenky. I'm broadly working on Far-UVC disinfection. I started out in my current role looking particularly at hardware and ways to create Far-UVC light for the purposes of disinfecting the air at much higher rates as possible with other technologies. And since then I've moved to a bit more of a broader focus, still focused on indoor air and on germicidal UV, but not exclusively on hardware.
Interesting. So why was hardware the initial focus for you?
So I started out about at this point a year ago at Convergent Research, which is an organization that launches focused research organizations. And I'm going to describe focused research organizations as you know how there's some startups that are actually like terrible ideas because they are basically just research projects and they're not profitable at all, even if they're interesting research projects? We're like the Y Combinator for that. But specifically focusing on projects which will unbottleneck a significant amount of things within a scientific field or otherwise, are more than just an average median science project. We want just the really important ones. Now, I say we, what I really mean is my colleagues, because I don't really do a whole lot of the operational management of that. I was purely there on the biosecurity team to scope out, is there an opportunity here? What are the bottlenecks? And as to why that's kind of why hardware is because at the time, back in summer 22, there was a bunch of money for this stuff, and there were multiple organizations kind of pursuing all elements of this problem in Far-UVC, of the safety, the efficacy, all of this stuff. Whereas convergence research, relative strength is that We have a lot of exposure to hard tech and deep tech. A lot of it's a very engineering focused sort of thing. And so we figure, these lamps right now, they're damned expensive. We're going to focus on the hardware and see what's the pathway to a solid state Far-UVC emitter. Because, we didn't really think it was the most important thing, but we thought it was the thing that we would be best at addressing. And essentially, two things happened. One, something happened, and all that money went away. And two, as kind of I got deeper and deeper into the research, what seemed like an intractably difficult problem of make a solid state high energy emitter turned into, oh, this is actually quite doable. This is actually just not a bottleneck. The real bottleneck is that the market's not really there yet, and the things that need to be done are mostly not directly working on the technology because, there's enough kind of technological talent and engineering talent that is interested in this stuff that, there aren't necessarily any bottlenecks at all, really, other than lack of a market current, as it is kind of a very new emerging technology that not a whole lot of people know about yet.
Yeah, interesting. Yeah, well, I want to step through each of those things. The sort of the technology where it's at now, and why the solid state seems likely to just happen without too much intervention, and then what other things are necessary to get Far-UVC to market. But I guess to step back to the beginning, I'm curious how you developed an interest in biosecurity and indoor air quality to begin with.
Why biosecurity? Well, this is going to be kind of a somewhat tedious story, but essentially, my background is in physics. But while I was doing physics, I kind of had this fantasy in my head that I was going to do my physics degree and then I was going to go to medical school because, as from my teens onwards, I was like, I want to be impactful. I want to have an altruistic career. I know I'll be a doctor and work in the developing world, or um, emergency rooms or something. And I didn't really get a chance to examine this kind of assumption until I, in fact, finished my physics degree, which I love doing, and realized, okay, time to actually get going to medical school. At which point was also around the time I was not, I guess, I don't know if it was the first time I had heard of it, but it was the time where I started getting more involved with effective altruism and essentially discovering oh, my assumption about the relative impactfulness of directly working as a doctor was not a good assumption. And also, I discovered I did not like medical school, and I was not sad to leave. But it did leave me in this position where I had a physics education and about a year of med school under my belt, which kind of made out of, the big problems in the world, right? What are the ones that a medical education helps you with is kind of naturally leads you to biosecurity. So in a sense, it was very path dependent. And so perhaps when I talk about why I currently think biosecurity and pandemic prevention is really important, that might just me being totally biased by my own path dependence and justifying decisions that I sort of made in a kind of very stepwise fashion of what's the next best thing I can do. But I think the nice thing about pandemic prevention is, one, the ceiling is high. Pandemics could get very, very bad. So the expected value of making them less likely is quite high. And we don't need to get too into what exactly very, very bad means. But I have kind of enough molecular biology to get really nervous about the increased availability of synthetic biology tools. But also a lot of the things that make extreme pandemics less likely also just make cold and flu less bad. And I think that includes quite a lot of the engineering controls that I got interested in, and that includes indoor air improvement, PPE, personal protective equipment, masks, and other things like surveillance potentially. But essentially, since this is high impact engineering, the two really engineering-based controls you can talk about that aren't pure biotech. Because at this point, I've kind of admitted to myself that I am not a biologist. I self-describe as a physicist against biology. We would like to use physics and engineering to prevent biology from happening to people. So, you're looking at kind of engineering controls for the environment or for the individual. For the individual, we're looking at PPE, and I did spend some time working on that. And the reason I moved away from that was that people don't like masks. They don't want them. It is a hard product to sell. This actually makes working on PPE for pandemic prevention significantly less tractable because it's, even if you can make a much better mask, and you definitely can, and there's people who work on that, and it's really important. But, once you've built a much better mask, what do you do with it? Who do you sell it to? People got so sick of it during the COVID-19 pandemic that it's kind of like, it seems quite intractable as a social problem. Now, with indoor air interventions, of course, it's harder in the sense that you have to convince not just the individual to do something, but it's also easier because you don't have to convince individuals to do something. You can just change the environment and create like lower risk. You can do it built in, totally passive, and ideally pathogen agnostic, in a way that doesn't actually require any personal change from anyone. You just do it once and then you're done, or you make it part of the infrastructure and then you're done.
The problem that we're trying to solve here is that people really don't like wearing masks. If you want people inside in like a pandemic situation, then if it's still in the high contagious stage pre-vaccine, or and there's high risk of people contracting the virus, the way to stop it at the moment is for everyone to wear masks, and even then that's not necessarily 100% effective. So there must be some better way, and Far-UVC potentially promises a better way, or poses a better way to do this.
Right. Yeah. So I can get a bit into that. So Far-UVC, that's the far ultraviolet C. It's the part of the electromagnetic spectrum that is between 200 and 235 nanometers. It's a subset of the broader wavelength of UVC between 200 and around 285 nanometers. Normally, the spectrum is totally filtered out by the atmosphere, so you don't get any of it on Earth from the sun, because it's filtered out by the ozone layer. However, that's also why it is quite germicidal. The living things on the surface of the Earth are not adapted to it, and this isn't new. So this has been known since the 19th century, and germicidal UV, GUV, has been in use for, I think at this point, nearly 100 years. Primarily the near UVC, primarily the 254 nanometer wavelength, and that is already widely used for water disinfection, and it's also in the middle of the 20th century was commonly used for air disinfection as well, except this was used in a system called upper room GUV, where you have your germicidal lamp, but you're pointing it at an unoccupied area of the room, and then you rely on the circulation of the air in the room to reduce infection rates. Because people don't really think about this, but room air tends to get mixed together quite fast. If somebody lights up a cigarette at the other end of the room, you're going to smell it pretty quickly. You're going to see the smoke spreading. So, and it's worked really well. We have, decades of data of, it can even work to slow the spread of measles, which is about as infectious and as transmissible as a pathogen can get. And we sort of just stopped using it. And why did we stop using it? Basically, vaccines got good, and we just didn't care anymore. There was like a little bit. It was used a little bit more to control tuberculosis at homeless shelters, and then tuberculosis also just went down. And yeah, so it's this great tool that essentially we're not really using, partly because it is labor intensive to install. You have to come and have a technician come in and install it like in your building, and also like do all the measurements correctly so that none of the UVC is getting into the occupied area of the room, which you don't want, because so 254 nanometer UV, it's not going to give you cancer, most likely. It's the skin cancer spectrum is actually peaks in the UVB around 315 nanometers. But it is it is a skin irritant and an eye irritant. Photokeratitis, eye reddening, and skin reddening are all possible. And that's just and there were in fact incidences, actually as recently as 2020, where a school in Georgia tried installing upper room GUV, and they just installed it wrong. They installed it as a normal lamp. I don't think anyone was hurt, but it did freak people out, So these sort of like operational challenges kind of stymied the use of GUV particularly widely. But more recently, we have discovered that the far UV wavelengths, shorter wavelengths, are also germicidal, but they don't have these negative effects on mammalian eyes and skin. And that's because the fundamental mechanism of inactivation starts to change. So for conventional GUV, the way it works is primarily through absorbing into DNA. 265 nanometers is the peak absorbance for DNA pyrimidines, that's the C's and the T's. And essentially, you only need to absorb a couple of photons for the DNA to create these kinks in the DNA, and that completely prevents a pathogenic organism, or any microscopic organism, from continuing to propagate. With far UV, we know that it's a lot more protein mediated. It's heavily absorbed by proteins. That's where the peptide bond absorbance gets really high in the far UV. And we don't know exactly how the inactivation mechanism works yet, but that is essentially why it can't really penetrate too deeply into human tissues. You have a lot of dead skin, you have the mucin layer in your eye, and it just can't penetrate. But it can penetrate viruses and bacteria, and when it absorbs into their proteins, that is not good for them. So the idea is, what if you could just have this everywhere, all public spaces? Sort of is just, in the same sense that we have the GUV systems for water, and you can have air that is by design as clean as water in the developed world. And this is quite attractive. One, it's a very I think utopian progressive vision. It's imagine no more cold or flu ever. And it doesn't actually require anyone to do anything. And it's hypothetically, because you can just screw it into a light bulb, going to be a lot easier to install, and that's going to save you a lot on the labor costs. I think the economic calculus is a little bit different in low and middle income countries, where labor is cheaper, at which point it might make sense to focus more on the conventional GUV, just because it's the lamps that produce conventional GUV they're low pressure mercury lamps. They're essentially fluorescent lamps that are without the fluorescent part. And they're quite efficient. They're dirt cheap. It's a very mature technology. It takes a little bit of brains and effort to install them. And that's kind of it's not an insurmountable problem, but it does mean the economics are different between countries.
Yeah, really interesting. So basically, Far-UVC presents an option to effectively wipe out at least airborne pathogen transmission in indoor environments, potentially eradicate cold and flu, and mitigate sort of some of the risks, at least from worst case pandemic scenarios. Um, I guess what are the bottlenecks in the current technology that are preventing it from becoming something that's just, I guess the long-term trajectory is like working into building codes and have it a requirement for every like building space that has occupancy over X number of people to have these lamps installed in public or high traffic areas or something like that to prevent pathogen spread. So what are the sort of the bottlenecks here?
A lot of it is that people just don't know about it, and the market is small. So there's pretty much one manufacturer of the far UV light sources that it is, kind of head and shoulders above all the competitors. And there are like the number of units they've produced is in the low tens of thousands. This is an extremely niche market. There's been a lot of investment, been a lot of interest, but so far not really any profit whatsoever. So it's partly it's that, it's a public outreach problem. It's that. The other part is that there are still some open research questions, right? There's more safety studies to be done, and from like a lot of perspectives. There hasn't been a ton of research. This is an emerging technology. I personally am convinced on the merits of the evidence. I have one at home, and I think it's quite unlikely that it's going to cause anything that is like in any way worse than the normal disease risk that people face. But if for anything on like wide populations to get like the endorsement of any sort of public health agency, you kind of have a much higher bar for evidence of like all groups, all like vulnerable groups, the elderly, children, people with photosensitive skin, all these things. So there's just like a giant slog of data to be collected. It's not just interactions with humans. It's how does it interact with insects, with plants, with different types of surfaces. Like we know UV yellow surfaces, and that far UV is like a bit worse than longer wavelengths. Is this so? Like which plastics? Is it fast enough to like be a problem? All these things. There's also an air chemistry question. So below 253 nanometers, UV does produce low levels of ozone, and it's been not. And then ozone can then react with volatile organic compounds that exist in the air. Anytime you're cooking, you're putting VOCs into the air, burning a candle, any sort of cleaning product, and then ozone can react with those to create particulate matter. The real question is it enough to matter? If you have, and I think quite plausibly, no, it's not enough to matter, especially even if you're using very high doses, and higher doses give you faster disinfection rates without apparently compromising skin safety. The safe dose for skin seems to be quite a bit higher than the current recommended limit. But yeah, so does the produce enough to matter? Like in what settings? For example, VOCs are quite a bit higher in homes than anywhere else. Schools and offices look very similar just because you don't usually cook at the office. But yeah, so there's a lot, and especially, we haven't even gotten into mitigating efforts. Like if you slap a portable air filter, is this even a problem at all? Quite possibly not. So in terms of like standards development and regulation development, all of that needs to happen. As to why can't you go and buy one on Amazon right now for like $200? That is more of the public outreach question. And I think in terms of technology development, all of that is going to very readily follow from this sort of market development.
Right. Interesting. So it's possible to buy the lamps and install them, obviously, because you've got one at home. And so there
Well,
is, or it's a little bit harder than that.
it's a little bit harder than that. Yeah, I actually, you can't really buy them directly from the manufacturer unless you are a business. The story of how I have this one is a bit of a tale. Yeah, but it is difficult. It is rather difficult to buy them, especially for a reasonable price. You can get one for like $2,500, which is going to be a pretty massive markup. And there are more people entering. Acuity had one on sale for about 400 or 500, but you can no longer get them. And
these are like the gas lamps, right?
so these are actually krypton chloride excimer lamps. They are conceptually similar to a gas discharge lamp, like a fluorescent lamp, in that like you have a high voltage excitation of some sort of gas. And this effect is, this is not a new physical effect. I think it was just studied in the 60s onwards, and and they're widely used for like other UV applications, like curing, for example. It's not a mature technology though, just because there hasn't been much of a market application until quite recently. So it's quite a bit more niche compared to like low pressure mercury lamps, which, and to give you an order of magnitude estimate of the costs here, a low pressure mercury watt will run you about $2 to $4 per watt of output. A krypton chloride excimer is going to run you a couple of $1,000 per watt.
Oh, well. Yeah, that's a big difference.
Yes. And also for context, if you look at the white LED, you're looking at more like 10-15 cents per watt.
Right. So there's like about what's that, 3 to 4 orders of magnitude price reduction that's really needed to make it comparable to existing like LED fixtures that people can put in their homes and in the office.
Yeah, it's and I think they're definitely going to get cheaper. I think the cost floor is, it's nowhere near that $2,500 that you can go and buy one online for right now. But it's not going. But it's not going to get LED. The current excimer technology is not going to get LED cheap ever. Like it's just the manufacturing process, and then the bill of materials and all these things, the supply chain, all of that. All of that is sort of not indicative of the sort of dirt cheap cost flooring that a solid state technology can have.
Right. And so in terms of the solid state technology, how you mentioned before that's looking very promising and looking like it'll just be likely to happen because there's enough like scientific expertise to do the research. What's that sort of roadmap there look like for that technology coming down in price, or even does it exist at the moment as a solid state, or is it still sort of an unanswered question or a yet to be answered question there?
You can technically buy an LED in the Far-UV. It's going to be even worse costing per watt than the excimer technology, and it's going to have much worse reliability. When I think that solid state emitters for Far-UV are coming, I don't actually think it's going to be an LED, and I'm not actually sure that we'll ever have a native LED in the Far-UV range. And this has to do with, at this point, you're looking at around 6 electron volts to get the right wavelengths out for your band gap of any semiconductor. At this point, it is almost an insulator. And it is extremely difficult to get a diode to behave as a semiconductor at the amount of it is damn near close to just an insulator, and that just creates so many problems. They're not totally impossible to overcome, I think in 10 years, there will be a lot of progress already, especially as progress is made on device packaging, on fundamental understanding of the defects of the material that's used to make them. But I think this, even if you can get reasonable power output, it's tough to get the reliability up. And I think there's big open questions about, will you get to anything like 10, 25,000 hours out of something that, these are very high energy photons that you're trying to emit. So it's tough. You're essentially using the same material system that underlies the blue LED, and you're pushing it to its absolute limits. And there's just not that many people working on it. There's like a couple of groups, and it's always possible that there will be a huge breakthrough. I personally think that the thing we'll see long before we see a native LED on aluminum gallium nitride, which is the material system that you're using at these band gaps. It's a lot easier to just start with a blue laser and double the frequency using some kind of nonlinear crystal. And you're essentially putting in two blue photons of, say, if you start with 450 nanometer blue photons, putting two of those in, you can get out a 225 nanometer photon.
Yeah, interesting. The sort of frequency doubling technology is relatively developed as well, from my understanding, I think, because I know in scientific lasers that's used to, so for my experience, I used a 532 nanometer laser, and I'm pretty sure that was frequency doubled or something, or one of the other ones we used were, yeah.
So not so much anymore. There's been a lot of progress, but for a long time, green LEDs were in a similar position where the material system, like from both ends, that's AlGaN and InGaN, just had it was too long a wavelength for one and too short a wavelength for the others. So it was really hard to get a high efficiency green LED. And that's, changed recently. I think there's been a lot of improvements. But essentially all green lasers are actually frequency doubled infrared lasers. Now, the problem with frequency doubling is that if you're doing external coupling of the nonlinear crystal to the source laser, you are getting massive phase matching problems and losing a lot of efficiency. So it has to be... it's just a real pain in the butt.
So for listeners who are interested in diving a little bit more into this chip technology or interested in going into the field, are there any, I guess, courses or resources that you'd recommend for people to understand more, or what sort of backgrounds would be useful for working on this sort of technology?
Certainly photonics, and look into courses onto nonlinear optics. I think something really important is, semiconductor processing, materials processing, understanding, and I think broadly just understanding the scaling effects of, how do you scale a technology like this? I think there's probably a lot of alpha in various kinds of research in here.
If people are interested in going into working on the technology, that's one thing. But if people are interested in using their skill sets most effectively, then what would you recommend people be thinking about instead then?
Yeah, I'm thinking about in terms of, if you are some kind of a material, you're interested in materials, you're interested in like processing and manufacturing of the sort of thing. One big need that we identified actually at a workshop that we held recently is in device packaging, and also in potentially novel materials, not for the device itself, but for the filtering and the filters and the reflector coatings that are involved in the device components. What exactly that involves, I'm really not sure. I think what I found is that to kind of make progress on anything, you really need to get really deep in the weeds of it. But for example, the nice thing about this like laser frequency doubling approach is that um, you're getting essentially monochromatic light. So with Far-UV, you want wavelengths in the right range and no others. If you go too long, you start getting potentially more penetrance into human eyes and skin, which you don't want. Everything, so they have to be filtered. So krypton chloride excimer lamps, they emit primarily in the 222, but they have very low levels of emissions elsewhere. And even those low levels can be quite bad. So they need filtering. And there's only so many, there's only so many types of filter materials available out there, and they could be better. I think the way that you and I think there is in fact room for kind of novel material discovery and development for this application. Uh, it's very far from ideal, and in that sense, unless you're doing a laser, which may or may not actually end up being the most cost-effective technology for this, if you're needing to be filtering, right at this cutoff, I think having high-quality materials there is quite important. Similarly, this also goes for reflectance, where if you want to package some sort of emitter, you need something that reflects well in these very distant and high energy wavelengths. And yeah, the material availability there isn't great either. So that's kind of another thing to think about.
You've given a bit of an overview of where the actual technology needs to go, or where it could go rather, to sort of bring the cost down. What is the cost for if everything goes well, if the frequency doubling works, for example, or if there's some solid state sort of breakthrough, what are the current estimates on the cost for, say, 20 to 30 years from now?
I think 20 to 30 years for solid state, couple of bucks easily, per device. I think per watt, potentially it could be a couple of bucks per watt. It entirely, with solid state, it entirely depends on scale, right? If you're doing runs in the tens of millions, hundreds of millions, then sure, anything's possible. And then your main questions are, is the process it's very early right now, so it's hard to even say what's going to be the ultimate winner. So right now I'm very optimistic on doubled lasers for the next 5-10 years. I think it's going to be tough for a traditional LED or even alternative design LED to beat that on that time scale. But 20-30 years from now, who knows, right? I mean, people I think as we saw with the white LED, when there is the giant market, there's a lot of ingenuity that happens. So it sort of all depends on, it essentially just all depends on whether the stuff takes off. And I think we're in a very critical period right now of, creating that. I mean, people are already sort of forgetting about the pandemic. Nobody wants to think about it, even though, it's still quite bad. I've been working on this cost estimate recently, and airborne, just cold and flu alone incurs something like $1 trillion in costs a year, and COVID represents about a massive multiplier on that. It's maybe 3 to 10 times worse.
Wow.
So yeah, it's really quite bad still. Lockdowns are kind of still more costly, and it's not really a social emergency anymore. But it's I mean, COVID-19 really just sort of made everything a lot worse. But it's hard to get people to even really notice. So yeah, it's do we still have enough momentum to create this market, to make this take off, to get people excited about it, and insist that it be a part of the infrastructure? Because if that happens, then the cost scaling is going to be great. I think solid state has massive potential. If that doesn't happen, then I think even some of these technologies I've been talking about that are on the horizon and quite, they're not particularly speculative at all. I mean, they might not take off at all either. So it's we're in a very hingy moment, I think.
So if we need the market in order to bring the cost of the technology down and reach those economies of scale, what are the next steps that need to take place to get that market up and running? And really, what are the bottlenecks there?
Yeah, I mean, funding the research, one. I think kind of your usual, sort of activist activities of making a lot of noise about it, convincing other people. There's public outreach, science communication. I think there's probably some, an initial market could be large, say groups of immunocompromised people. There's a community of like transplant recipients that are essentially still living in 2020. I think just for people like listening and like interested in this, you would just want to get familiar with the technology, get involved. Like it's a very small community right now. I probably know everyone in it, and that's not because I know a lot of people. It's small. So, I think just it's an interesting question, because how do technologies get adopted? Is there How does that actually work? I'm realizing I don't really know this. What's like the critical question? And I don't know that I can even answer the question about bottlenecks, because it's not clear that there really is a bottleneck so much as just a bunch of cumulative effort that needs to go into it, and a lot of like cumulative attention. And it's for one thing, one thing that makes it hard is that a lot of companies will say offices and other entities, they'll say, well, where's the study that shows that it works? And it's actually extremely hard to do that unless you have an isolated population. So, I mean, there's been some talk about doing a study on an oil rig, like they install, or like say on a cruise ship, or any sort of a situation where there is not a whole lot of people coming in and out. Because if you don't have an isolated population, it's very difficult to see an effect, because even if nobody gets infected while there, if you have someone leave and then get infected while they leave and then come back, then that's going to reduce make it look worse than it really is. And that's kind of the other challenge, is that it's not very realistic for people to be isolated all the time. Where you really start seeing benefits is when you get a certain level of coverage. Like if you have disinfecting lamps at some critical percentage of public spaces within, say, one city or one town, then you're going to see a massive reduction, but it's not going to be linear. So adoption is hard, right? Because you're not an office or other public space that opts to buy the stuff and install it. They're not going to see commensurate benefits until everyone else does it. So it is a bit of a coordination problem. And I think, at this point, it's much less of an engineering problem, so much as a social engineering problem, where you're looking at tools advanced market commitments and other sorts of weird tools that better price in externalities. And it's it's sort of, and then you're in a similar position as the position I talked about earlier with respect to PPE and masks, where yes, there's an engineering problem, but the social problem is much harder. It's maybe the kid. There's a lot of cases like that. On the other hand, I do think understanding the engineering problems and the physical problems is extremely important for being an effective advocate. There's even the committees and the organizations that are kind of in charge of this, they don't really know a whole lot about what the deal is with Far-UV, and then kind of, what's the fundamental mechanism of inactivation? What are the, considerations for real world implementation? All of that stuff is the sort of thing that, engineering know-how is quite important, just to be an effective advocate and to be the person helping write the standards. and talking to either the public or to policymakers about it.
Interesting. So if engineers are interested in that advocacy policy route, are there any companies, organizations, think tanks that they should be looking into, or is it still very early for that sort of stuff?
Well, One Day Sooner does have an indoor air project. So that's one group. I spend a lot of time working with the Oslo project. It's also it's an engineering nonprofit that is similarly, like, hey, we solve technical problems, but the social problems are much more important, thornier and more important. Um, and they're quite new, but they do great work. So that's someone to check out. You might consider, if you're already um, somewhat in the space, you might consider just straight up joining the ASHRAE UV committee. That's TC 2.9. I'm to understand it's quite boring, but it's potentially like quite high impact if you know what you're talking about.
And for context, there, the ASHRAE committee sets the standards for built environments in, I believe it's the US, right?
Yes, although you don't actually need to be an American to join it. Oddly
Oh,
enough,
okay.
even though it is the American Society for Heating, Refrigerating, and Air Conditioning Engineers, but nope, you don't actually have to be an American. It's very odd. They even have special programs for people to join if they're from a low-income country.
Fascinating. Yeah, I know we use, from my very limited time in an internship in the building services industry, we do, at least to some degree, use the ASHRAE standards in Australia or for some aspect of design, but I can't quite recall. So I know it is used outside of the US to some degree as
Oh, yeah,
well.
that's interesting.
Yeah. Yeah, I think there's a couple that we might draw on, and I think there's maybe another set of standards for Australia as well. But I'm getting pretty far out of my depths of understanding here.
Mhm.
um, so, where would you be most excited to see more engineers working in Far-UVC?
I would be excited to see more, just broadly more like engineering applications research for like how do you build an optimal system for a given indoor space, how do you like make this as painless as possible to install. I think, in fact, one thing that's really missing, we have safety standards there, or recommendations anyway for exposure. We have UL certifying like actual physical products. What we don't have is any kind of standard for um, how much output does this device need to be doing to actually work. Like there's no effectiveness standard at all, and I think this is actually a big problem because a lot of the manufacturers right now, they will sell you a lamp that is not going to be outputting in nearly enough dosage to do much of anything. And this is because the standards are actually different between the safety standards for exposure. They're different between the U.S. and Europe. The U.S. actually updated the for UV exposure levels in 2022 by quite a bit. And if you're constrained by the new standards, then you can get extremely high levels of disinfection in quite short periods of time. But the old standards, which are also still in effect in Europe, which is I think governed by ICNIRP, the International something of non-ionizing radiation, something like that. Whereas in the U.S. it's ACGIH, the American Conference for Governmental and Industrial Hygienists. I'm very impressed with myself for having remembered so
That
many
is
different
impressive.
professional society acronyms. Um, so manufacturers are in kind of this twilight zone of like, which one do I use? And they're generally being quite conservative because you're in trouble, especially if you're, in Europe, the standards are law. It is illegal to sell something that will expose people to more than that amount, which is, frankly, way too little to do a whole lot for airborne infectious aerosols. Like, it'll do something, but you may as well just get a HEPA filter. Um, but and there's nothing that says that you can't sell something that is like not powerful enough. So I think that's one big missing part. And I think just there's a lot of system design work to be done on both. How do you make a system that is for sure safe, easy to install, and actually going to work? And there's quite a lot of work that needs to be done on the validation part. It's like how do you actually verify that it's working and actually getting you the disinfection levels that you want? Like it's actually pretty much an unsolved problem right now. It's even especially for UV, because you can at least use some proxies, right? If you're measuring just like how well is my ventilation system working, you can track CO2 levels. And if there's like a bunch of people in a room and the ventilation rate is too low, that CO2 level is going to creep up, and you can use that as your proxy for infection risk. But that CO2 is not going to track filtration efficacy. So you can maybe look at something else, like you can look at some other type of particulate that's maybe not dangerous, but like is removed by filters that also are known to remove infectious particles. But with UV, you can't even do that. It's like, how do you how do you do that in a way that is like robust and accessible? And you can't really write a standard if like the people who are going to be implementing that standard can't easily interact with it. And I think that's going to be really crucial. So I think that's ultimately where it's going to take a lot of engineering manpower to work out on that end, but also just on the actual implementation end. It's going to involve like a lot of working with building codes and the like electrical design firms and things like that. And it's going to be I think it's going to be a longer haul and overall tougher than actually making an emitter that works effectively. I think we'll get those for sure if we can make the market for it.
Yeah, I think it's really interesting thinking about the full system there and thinking of, what other things around the core technology need to be in place in order for this to be adopted. Because it's kind of easy to overlook the fact that, well, if there are standards, the standards need to be testable. And if they need to be testable, there needs to be actually some methodology by which you can go into a building and measure the level of pathogens or measure some proxy for that to understand if the system is being installed. Even just from if we in a scenario where we already know that the technology works, you just need to verify that it's been installed properly and it's actually switched on and is doing the job that it's supposed to be doing. In the same way that, as you were saying, ventilation systems, if they're installed or as they're installed and commissioned, they're tested to ensure that they're working correctly.
Sometimes.
Sometimes. Ideally, in an ideal world. I've got a couple of questions around, I guess like safety concerns before we move on to talking about your experience of working in this field. You've mentioned the potential ozone issue, but that might be not that big of an issue or just needs some more research around it. Are there any risks of like selection pressures caused on or applied to pathogens causing sort of UVC resistant pathogens, similar to the way antibiotics can cause antibiotic resistance?
So this was a concern I also had when I first learned about this technology. And, for a while I was like, almost like I sort of tabled looking further into it just because it seemed like this could be a pretty big problem. I'm kind of no longer all that worried about it for a couple of reasons. One, we have a lot of data about, UV induced resistance, and it seems not a whole lot of it. I think it's one of those things where, in principle, I guess it could happen, so we may as well check. I don't think it is broadly regarded by the UV community as a serious risk. I could in principle imagine, but I will say, that a lot of that will have been for the conventional GUV that primarily inactivates the DNA. With Far-UV, it's a lot less clear what the exact mechanism is, so in principle it's possible, but it is sort of such a fundamental inactivation mechanism. You're really targeting the very building blocks of life that it's going to be really tough for pathogens to develop resistance to it. One thing I could imagine is that if you're a bacteria and you're getting pelted by these like high energy short wavelength photons, one thing you could do is develop a higher propensity to form biofilms because Far-UV doesn't penetrate biofilms very well. They're basically, thick protein coats that will make a pretty good defense against Far-UV. Viruses, though, are probably SOL. It's they. I think it's going to be, and I wish my virologist colleague was here who could probably explain this a little bit more clearly. I'm essentially just not that worried about it because viruses need to be replicating in something in order to experience do this, and that's not where you're going to be getting them. With bacteria, yes, it's in principle possible. I think there are experiments ongoing to be a little bit clearer about like this doesn't happen. But it's also, if anything, I would be a little bit more worried about the overall changes to the indoor microbiome. And the reason that that concern there is mitigated is that there's going to be lots of surfaces that the light never touches. Any underside of a table, anything that's in shadow, isn't going to be getting disinfected. And surfaces generally are a lot more resistant to, you need a lot more dosage to get surface inactivation than aerosol inactivation. And this is also the reason that I'm not terribly worried about the disruption of the skin microbiome, which is another safety concern we haven't really touched on yet. But yes.
Right. Yeah. I was going to ask about the skin microbiome because that seems like it could potentially be bad in unknown ways if it did disrupt the skin microbiome.
It would be bad in fairly known ways, actually. Skin microbiome disruptions are, but the thing is, the skin microbiome is quite hardy. You have quite deep pores. You have a lot of you have wrinkles, you have folds. It's the reason that you need such a much higher dose of UV, of any wavelength, to disinfect a surface is that there's just a lot of places for pathogens to hide that there are not available if it's in an aerosol. Your skin microbiome gets disrupted every day. Anytime you wash your hands, anytime you take a shower, anything like that, really.
And I suppose you're also wearing clothes in most scenarios where you're under UVC light or Far-UVC light.
Yeah. So ultimately, yes, it will be a disruption. It's possible that like an additional insult to the skin microbiome, especially for like some individuals, there's like massive variation between individual skin microbiomes. So I'm not saying it's completely impossible, and it won't be a problem. I think it's also ultimately not going to be an irresolvable problem. And as far as I know, all the data that's been, I've seen some unpublished data, essentially shows no difference in microbiome of the skin when exposed, even long term. We do have some like long-term exposure studies of hairless mice. So yeah, this is certainly another thing that I worried about early on, and then essentially just kind of like was convinced that was not going to be as big of a problem as I initially thought.
Yeah, that's interesting. I think that does, make me feel a little bit more reassured because those were kind of the main concerns that I had on initial reading and sort of research into the technology. But I think one thing that your response there sort of clarified for me is that this technology is really focused on neutralizing airborne pathogens and less so on like disinfecting surfaces.
Well, you can use it for surfaces.
You just need
I
more
think
or higher power or longer exposure times.
either one, right?
Yeah.
It's all by dosage. It's but if you look at kind of the historic, like I said, GUV is not new. If you look at sort of the inactivation rate tables for different pathogens, like whether on air or on surface or in suspension, and the surface inactivation rates are just like orders of magnitude worse than in aerosols. Like, trying to get rid of a virus in the air is sort of the ideal circumstance to use UV. So, and ideally you want to use a relatively high dose, as high as you can get away with, really, and like still like maintain safety in the air, because then you get disinfection faster. You could even imagine like in principle, this is not necessarily something that I would advocate for in like public spaces, maybe as some sort of emergency measure. You could even imagine like turning it up high enough that as soon as you breathe anything out, it's inactivated within 1 second, and just at this point the air is so sterile that it's unless you're standing like 1 foot away from somebody, there's like no way that you're going to infect them. And that's kind of a very like edge case, like boundary condition. And I think you would need something like 40 times higher doses that are currently maximally allowed, even under the new ACGIH TLV standards, to achieve that. But in principle, it should be possible. Realistically, you're operating in far lower doses than that. Quite possibly just doesn't do a whole lot to the surfaces in the room at all.
Yeah, but that seems kind of okay to me, because we know how to disinfect surfaces. It can be done, and we know that, or at least I know I personally became hypersensitive of any surface I touched during sort of lockdowns and peak sort of COVID concerns. So, hand sanitization and hand washing became very like, front of mind during that period. And that kind of, I guess, is maybe not a fully solved problem, but the relative sort of degree of air like purification is much less solved.
Well, I think it's a lot of the concern over, surfaces and fomite transmission. A lot of that, I think, is now sort of recognized to be pretty erroneous, where more and more pathogens, not just COVID, but also, flu, various colds, are kind of believed to be likely airborne rather than significantly mediated by surfaces. Not the case for something like norovirus, which is like quite hardy on surfaces. But a lot of these respiratory pathogens, you're really worried about the air and person-person transmission that way. Whereas, yeah, with surfaces, I think it's remained sort of unclear how much like additional benefit you get from perfectly sterile surfaces for a lot of these common pathogens. Still worth doing, but probably on net, we're worried way too much about surfaces and droplets and this whole silly 6-foot thing of social distancing. I think that has been like massively overrated relative to just improving the indoor air quality and with respect to infectious aerosols specifically.
That's interesting. Yeah. I guess on a personal level, how have you found this type of work or working in Far-UVC, and who would you sort of recommend it to?
Ends up being quite cross-disciplinary. So, as someone that's, I get to touch a lot of different things. I have kind of a weird job right now, where, I'll be doing like a very high level economic analysis sometimes, and then other times I'll be doing like a very low level aerosol simulation. So I think it's a good place to be for a scientific generalist. It's quite a niche, so it's it feels good to be aligned. It's a lot easier to make an impact when you're in a small niche area that could potentially be quite important. So yeah, I mean, I feel good about what I'm doing. I think a lot of what needs to be done is just like dead boring sort of stuff. And that makes me, sort of makes people less keen to work on it. Yeah, I mean, when I say dead boring, and I mean that kind of more in the social perception rather than personal level. Um, I find it quite easy to get into the rabbit holes of like figuring things out. Um, Overall, I kind of miss having the ability to tinker a bit more. Hopefully, I'll be doing more of that in the near future. Um, but yeah, I think there's not really any such thing as working on Far-UVC per se. I think it's going to be highly dependent on exact role and all those usual things. Yeah.
Makes sense. Are there any other technologies on the horizon that you think are interesting or are worth investigating more outside of Far UVC for solving sort of similar issues around indoor air quality and pathogen transmission?
I don't know of anything that's quite as promising, but I think there is a lot of potential in exploring it. I mean, one technology that I'm aware of is um, microwave inactivation of aerosolized pathogens. I think it's less promising than GUV for a number of reasons. Um, that um, that is to do with it's an even newer emerging technology that I would love to be proven wrong when I say that I don't think it's very promising. But I think absolutely worth looking into, um, as well as like other things that I don't even know about really. um, I think volatilomics, the study of sensing the air, like volatiles in the air, for what's in there in the first place, and getting like really good air detection, I think is something worth looking into for sure. More on the surveillance side rather than engineering control side. And yeah, I think I would bet that there's a lot of crazy things out there for disinfection potential that just have not been looked at in depth, because it was essential. I mean, for a long time, aerosol scientists and infectious disease people did not talk to each other. I think this has been one really positive development that has arisen from the pandemic, is that now we realize that diseases are airborne, and it's important to understand how aerosols behave. Um, so that's been good, but it means that there is a lot of catch-up work to do. There's been a lot of to do about surfaces and things like that. And now I think there's just uh, there's tons of unknowns. So I couldn't even tell you what, but I would bet that it's going to be pretty wide open vistas.
Great. Do you have sort of a handful of resources that you recommend people refer to learn more about Far UVC?
Sure. I believe Chip Blatchley at Purdue is a lead author on. There's a 2022 paper that is kind of like state of the art. There's there was recently the first International Congress on Far UV Science and Technology that just took place last month. And all of those talks are now, I believe, available online. Um, so as far as general resources, it would be probably easier to put things in a link of some sort.
Yeah, sure. We can
Yes.
include anything you'd recommend in the show notes. What do you wish you had invented and why?
Ooh. I wish I'd invented some sort of how well is my indoor air quality apparatus working box that is cheap and good and installable like everywhere. This doesn't exist, which is why I wish I'd invented it.
Yeah, it's very fitting. I actually, in preparing for this episode, I was obviously reading a lot about Far UVC and indoor air quality, and started looking on Amazon for indoor air quality sort of measuring devices. And they're not super cheap, and they don't measure a whole bunch of things. All right. Well, before we finish up, then, where can people find more of your work online, or get in contact? Or are you happy with people to get in contact with you if they're interested in getting in the field?
Yeah, I'm certainly happy to be contacted. Where am I online? I'm mostly not. I do have a Twitter. I and I, that's probably the only professional facing ish social media that I've got. That's just Vivian_Belenky. Um, I don't have a website or anything. I keep telling myself I'm gonna get around to rebuilding it. I just have a domain name saved and I keep not doing anything with it. There's always been more important things to do.
And is the Twitter the best way for people to get in contact with you?
Just shoot me an email. My Twitter also has my Calendly link if anyone wants to just book a call to chat. But yeah, I'm always happy to be emailed.
Terrific. Well, Vivian, thank you so much for joining me.
Yeah, thanks for having me.
I hope you enjoyed that conversation with Vivian. For detailed show notes and valuable links related to this episode, please head to engineeredforimpact.show/Vivian. That's VIVIAN. The best way you can support the podcast is to leave us feedback. We want to make conversations like the one I had with Vivian as valuable for you as possible. So we use the feedback that you give us to help improve the show and make the episodes more interesting and more valuable for you. You can leave us feedback directly on the show notes page for this episode or send us an email. Thanks for listening and happy problem solving.